Okay, so good evening. So in this video presentation, we're just going to have a recall on the basic principles that we had in our strength of materials for shearing stress. Okay, and also including bending if bending is involved in the problem. So in this example, so first example, you have here a wide flange section has the following properties. You have the width of the flange to be 150 mm, modulus of, sorry, that should be, that is moment of inertia about x-axis is 108 times 10 to the 6 mm to the 4th, and then overall depth is 300. Your allowable shearing stress is 0.4 of the yield strength. Thickness of web is 9 mm. Thickness of flange is 12 mm. You have the moment of the area with respect to the neutral axis to be 380 times 10 raised to the 3 mm cube. And then you have the span of the beam to be 7 meters and your yield strength to be 248 mm. So your task is to determine the shear capacity of the section. Next is to determine the safe uniform load that the section could carry, and then to determine the shear flow of the portion of the flange 20 mm from the edge. Okay, so let's write down our information. So first, you have the width of the flange to be 150 mm. You have the overall depth to be 300 mm, and then you have thickness of web to be 9 mm, and then you have the thickness of the flange to be 12 mm, and that is also 12 mm. Okay, so for number 1, determine the shear capacity. Okay, so shear capacity of your section can be, or shear can be calculated in two ways. Okay, it's either you're looking for the average shearing stress. Average shearing stress, as we all know, is FV average is equivalent to the applied shear divided by, or the shear force divided by the overall depth times the thickness of web, while maximum shearing stress, FV maximum, is taken as shear times the moment of the area with respect to the neutral axis divided by the moment of inertia times B, or the width of the base, or the base which are the location of the, how do we define B again? B is defined as the width of the portion which you are analyzing. Okay, so let's take this two. Okay, so as per required, your required is to determine the shear capacity. You're given the maximum allowable shear strength to be 0.4 Fy. So let's just take both average and maximum shearing stress. So your allowable shearing stress, Fv, is equal to 0.4 times Fy, wherein Fy is 248 megapascals. Basically, that one is for A36 steel. Okay, so substituting values, you would have here your maximum allowable shearing stress is 0.4 times 248 MPa. Okay, that will give you a value which is equal to FV equal to 99.2 megapascal, or that is 99.2 newtons per mm square. Okay, so starting with your average shearing stress, FB average, so equating or maximizing the value of your allowable shearing stress, substitute that to this particular formula. We will be looking for the allowable shear. Okay, then substitute values for D and TW. So that would be what? 99.2 kilonewtons per mm square is equivalent to V over the width, or the depth of the flange, or the depth of the section, that would be 300, multiply that by thickness of web, that is 9 mm. Okay, then you have your shear. Okay, so for that, for using average shearing stress, you would have a value which is equivalent to 267.84 kilonewton. Okay, the problem did not specify whether if it is average or maximum. Okay, so let's just calculate for 2. Okay, next is substituting your allowable shearing stress to this particular formula. You would have here 99.2 is equivalent to V times the moment of area with respect to the neutral axis, that is 380 times 10 raised to 3, that is mm cubed, divided by, you would have IB. I for this particular section is 108 times 10 raised to the 6 mm to the 4th. Multiply that by B. Your B here in this section is taken here. Okay, so basically the width there is 9 mm. Okay, so with that, one equation with one unknown, you calculate for the value of V. V is equal to 253.74 kilonewtons. Okay, next is your maximum allowable load. Okay, for number 2, determine the safe uniform load that the section could carry. So, safe uniform load based from our tier of structures, if we have your beam to be simply supported, and then it is carrying a uniform load. Let's say the uniform load is denoted by W. Then again, from our problem, your span is 7 meters. Our objective is to determine the maximum value of W. Okay, so in this case, let's just take this one, your maximum shear, to be 267. So 267 as your maximum shear. In this case, since it is uniformly distributed load over a simple span, then basically your formula or your derived formula would be P or W times L over 2. Okay? So common sense will tell you that over a simple span having a uniform load of W, they will just be divided into 2. Okay? So you would have here 267.84 kilonewtons. That is your V. And then you're looking for W times the span of 7 meters divided by 2. Then you would have a uniform load W equal to 76.53. That would be in kilonewton per meter. Okay? And then last, you have here number 3, determine the shear flow of the portion of the flange 20 mm from the edge. So, going back to your figure, okay, you're looking for the shear flow of the flange 20 mm from the edge. So, this is the edge, 20 mm from that. You'll be looking for the shear flow of this particular portion. So, that is 20 mm. Okay? Now, the formula for shear flow, again, is from your strength of material. Shear flow is denoted by small letter Q, is taken as V times Q over I. Okay, wherein V is the maximum shear applied, I is the moment of inertia of the section, while Q here is the moment of the area being considered with respect to the neutral axis. So in this case, we can identify our Q, or we can assume, or we can have Q as, or V rather, as 267.84. Our I is of course 108 times 10 raised to the 6. And then we need first to calculate for Q before we can arrive at your answer for your shear flow. Okay, so calculating for Q, Q is equal to, that is the width of that, the width of this one, the width of the portion, that is 20, times the thickness, that is 12. Okay, and then times its lever arm. Lever arm would be taken from the centroid of that particular segment or that particular portion with respect to the neutral axis, the distance of the centroid to the neutral axis. Okay, so that would be how much? So you have here 300 Okay, neutral axis by common sense is at the mid height. So 300 divided by 2 is 150. That will be the mid height. And then the centroid of that particular portion is the mid height of 12. So that would be 150 minus 1 half of 12. That would be 6. So that would be multiplied by 150 minus 6. You would have a value of Q, which is equivalent to 36 or 34560 unit. That would be in mm cube. Okay, then you can now proceed to your shear flow. Shear flow is equal to, you have 267.84 times 10 raised to the 3, that is in newtons. Okay, so you convert kilonewton to newton. Our unit for shear flow would be in newtons and in mm. Okay, so times, you have 34560 mm cube, and then you would have your moment of inertia to be 108 times 10 raised to the 6 mm to the 4th. So you would have a value for your shear flow for that particular portion to be 85.71. Check your units. You would have here, you can cancel out 3 mm there and then 3 mm there. You are left with Newton per mm. Okay?